Okay, more on chemical formulas. All right, there's three main categories of chemical formulas. The first category, which most people are familiar with, are the molecular chemical formulas. And as I stated in a previous video, these formulas tell us the numbers and the types of atoms found in a chemical compound. And all I want to do here is provide some more examples. Only today I want to draw more comparisons between chemical formulas and empirical formulas and structural formulas. So here's a range of different molecules, and so far the ones that I've drawn here, the formulas that I've written down, are all covalent compounds except for this last one. Okay, this is an ionic compound, and we know it's an ionic compound because it contains metal paired with nonmetal, by comparison to these other compounds that only contain nonmetals. And just a reminder, hydrogen appears in two places on the periodic table, both on the left side of the table and on the right side of the table. And anytime you have hydrogen in a bonding mode, where it's bonded to another atom, it's considered a nonmetal. All right, and then we have empirical formula. And an empirical formula is a chemical formula that was determined by experiment number one, or observation, if you will. But it's a more specialized kind of chemical formula. It doesn't give us information about total numbers of atoms in a chemical formula or in a chemical compound. Instead, what it tells us is it gives us the lowest whole number ratio of elements that are found in a given chemical compound. So it's like your bare bones basement assessment of the type and the literal ratio in which that element appears within a compound. So what I'm going to do is we're going to go down this list of compounds that I just wrote down here in my molecular category, and we're going to determine the empirical formulas for each one of these. And the way that we do that is by dividing the subscript by the largest number that's going to give us the lowest whole number ratio of elements in that compound. So for this first particle, which happens to be glucose, the empirical formula is going to be CH2O. And how we arrived at that was we divided each of the subscripts that are in the chemical compound by 6. The next compound down, which happens to be acetylene, we're going to divide by 2, so its empirical formula is CH. The next compound down is called benzene, and we're going to be dividing that one by 6. Notice that both acetylene and benzene have the same empirical formula. In a previous video, you could see that a similar relationship between, we saw this before with glucose and a molecule called acetic acid. I might as well put that one in here too. So acetic acid is C2H4O2, and I'll address that one for the empirical formula when we get down to it. All right, so then we have P4O10, and that one is going to reduce to P2O5, And then we have the ionic compound, Na2CO3. And I would ask the viewer just to look at that for a second. The reason this is in here is to make a point. All right? Most ionic compounds, when you inspect their molecular formulas, what you find is that these kinds of compounds are already in their empirical formula. So I'm just going to write that down over here. It's Na2CO3. The reason for that is because with an ionic compound, when you look at their solids, which are crystals, these are simply vast arrays of oppositely charged particles, and the way that we arrive at the formula for an ionic compound is that we're taking, when we look at that crystal, we're taking the simplest whole number ratio of oppositely charged particles that still, where the oppositely charged particles still sum to zero. So for an ionic compound, most of the time, the empirical formula equals the molecular formula. And then finally we have acetic acid, whose empirical formula is CH2 and then O. And you can see that glucose and acetic acid have the same empirical formula. Acetylene and benzene have the same empirical formula. So there's a couple of take-home messages here that we need to establish. All right, the first is that different molecular formulas can have the same empirical formula as their base formula. All right, and the second thing that I'm going to say here is that in the case of most molecular formulas, they do not equal their EF. All right, that's an important concept. There are exceptions to this. The simpler the chemical compound, the simpler the chemical compound for a covalent compound, the more likelihood that the molecular formula is going to equal the empirical formula. But for anything that has any sort of complexity to it, the likelihood that the molecular formula is going to equal the empirical formula is not likely. All right, and the third thing is the MF, well, and I should stipulate that here. This is when we're dealing with covalent compounds. All right. Now, for an ionic compound, most of the time the molecular formula is going to equal the empirical formula, and that's when we're dealing with ionic compounds. All right. Now, we have an additional type of chemical formula, and that's a structural formula. And I'm not going to spend a lot of time on this, but what I want to do is point out the structural formula of a compound is distinct from these other two types in the sense that what the structural formula, the information that the structural formula gives us is it tells us about the connectivity. I'm going to write that word down. The connectivity between atoms. So if we look at acetylene, this is its structural formula, and you can see how the atoms are connected, the fact that there's a triple bond between the carbons, and so on. When we look at benzene, its structural formula looks like this. So it's a ring, it's got double bonds in here, we look at acetic acid and its structural formula looks like this. You can see it's got two different kinds of oxygens in it. What I mean by that is one of them is double bonded, one of them is single bonded to the carbon and then to a hydrogen. It's got what we call a methyl group over here where there's 3 hydrogens attached to this carbon. This is an acid and the acidic hydrogen is right here. All right, and then let's see, where am I at here? Okay, so we have 2 molecules left. And those are complex enough that I'm going to bring these in. This one is glucose. Just bear with me while I bring in the next one. And this is the P4O10. All right, so this is my glucose. You see it's a 6-membered ring and we've got these OH groups all over the place. This is actually a stereo view of the molecule. The hatch marks indicate this bond is going back into the plane of the board. That the filled in hatch marks are coming out towards you. And then this molecule here is the tetraphosphorus dicoxide. The P4O10, and you see this is a very complex ring, and this has got multiple ring systems within the ring systems. So the structural views, just to finish very quickly, show you how the atoms are connected and tell you something about the shape of the molecule if you have a little bit more information.